Assalamu alaikum and good morning. So last lesson, we looked at how the E cell value, basically E cell is a combination of two half cells. It's when you add the electrode potential E note of the reduction plus the E note of the oxidation. Or if you were to use a different formula, they would use E note reduction minus E note oxidation. But because of the way that I have taught you to always reverse the sign for the value of oxidation, so you don't have to have that minus sign and you just add them up. So what E cell can tell us is that when we have a positive value of E cell, thermodynamically it is feasible. That means it can occur. But of course, there are cases where they don't happen in real life for a few things, like maybe the activation energy is high or other things, okay? Another guide or rules that we followed last time was that stronger reducing agent will react with stronger oxidizing agent. You can't have a weak reducing agent and a weak oxidizing agent. Just to remind you again that the oxidizing agents are the species that gets reduced. So all the species sitting on the left of your data booklet, when you look at the electrode potential values, are your oxidizing agent, and all the species on the right will be your reducing agent. Okay, another thing that we have not seen yet, but you should know that if the forward reaction is feasible, then the reverse reaction is not feasible. I hope to show you later with one example where numerically it is proven. That means if the forward reaction, the E cell is positive, then of course the reverse reaction, the E cell will be negative. So these are some of the reasons why, even after calculating the E cell, to get a positive E cell, which by theory that it should happen, but sometimes it doesn't happen because of the high activation energy or because the conditions that we actually carry out our practical is not in standard form. So standard conditions are usually consist of a concentration of your ions to be in 1 mole per gm cube, your pressure to be atmospheric pressure, and temperature at room temperature, okay? Another reminder is that when we multiply the equation, usually for the purpose of balancing the number of electrons, we do not have to multiply the E note values, okay? So the E note values stay the same, whether you multiply it by 2 or you divide it by 2, or any other number, which is unlike your enthalpy change. When you multiply your enthalpy change, the value of your delta H also will be multiplied by the same factor. Okay, so we are going to continue with question 5. Will chlorine oxidize Fe2 plus ions to Fe3 plus ions? The first thing, the most important thing for you to understand is the question. Where they say chlorine, it means Cl2, not Cl minus, because Cl minus would mean it's a chloride, okay? And will Cl2 oxidize Fe2 plus to Fe3 plus? So I've already selected out my relevant half cell equation and the half cell values, the E note values, to help me answer this question. Okay, so as usual, if you can, you would arrange your values from the most positive to the most negative. The reason for that is because usually the top left is a strong oxidizing agent and the bottom left is a strong reducing agent. Okay, so I'll just label that strong oxidizing, and Fe2 plus would be a strong reducing agent. So here already you can see that it is a combination of a strong oxidizing and strong reducing agent. So it looks like they can react. Okay, if the question doesn't ask you for the value, the E cell value, then you could just say, yes, chlorine, okay, chlorine can oxidize Fe2 plus. So that means chlorine can react with Fe2 plus because chlorine is a strong oxidizing agent and fluorine, Fe2 plus is a strong reducing agent, right? However, if we want to prove this using E cell values, okay, we can do that by first writing down the equation. Okay, so we will write down the reduction reaction and the oxidation reaction. So we know that the reduction reaction happens to the most positive E0 values. So that means chlorine, the chlorine half cell has the more positive value, and because it's reduction, forward reaction happens, okay, to form 2Cl minus, and the more negative or the less positive will have in the reverse, will go in the reverse direction, which is the oxidation. Okay, so Fe2 plus to form Fe3 plus electrons. So before I can actually combine this two half equations, I can do that because one is reduction and the other one is oxidation. I need to make sure that the number of electrons are the same. So you can see here, I've got 2 electrons in the reduction and only 1 electrons in the oxidation. So that means I have to multiply the whole thing of my oxidation half equation by 2 so that the number of electrons now match. Okay, so 2 electrons being gained by the chlorine and 2 electrons being released by the oxidation of Fe2 plus. Another thing that I forgot to include is the value, the E0 value for each reaction. So chlorine in the direction of reduction is just plus 1.36, Fe2 plus to Fe2 plus, which is the reverse reaction, the E0 would be negative 0.77. Okay, so it's the same whether it's Fe2 plus to Fe3 plus, the E0 is also negative 0.77, or to Fe2 plus to 2Fe3 plus, the value of the E0 is the same. So to prove numerically that this reaction can happen, oh, sorry, I need to do one more step, which is the overall equation. Even though the question is not asking for that, okay, I thought that I will just teach you how to write down the overall equation. Basically, you just add your reduction and your oxidation. Cl2 plus 2 electrons, this is from reduction, plus Fe2 plus, which is from oxidation, to form 2Cl minus, which is from reduction, plus, sorry, I should use the 2Fe2 plus, okay, to form 2Fe3 plus 2 electrons. So I have to be careful. I have to use this 2 equations, okay? The reason for that is, as you can see, that when I have the same number of electrons on both sides, I can just cancel them out, okay? So to tidy up my whole equation, it comes out as this, okay? You should not have any electrons in your full equation, all right? The E cell would be just to add your reduction 1.36 plus oxidation, which is negative 0.77. And that should work out as 1.36 plus 0.77. 2.13. And because it is a positive number, then we can say, yes, chlorine can oxidize Fe2 plus to Fe3 plus, okay? That's how you prove it mathematically. There are a lot of things happening here, and you don't necessarily need to do that unless the question asks you, okay? So since we've got this question as an exercise, I will just, teach you other things on how to write down the full equation and how to find the E cell of the reaction, if it does happen spontaneously or not, okay? Or if it's feasible or not. Okay, while you are copying that down, I would like to go to the next question. Question number 6, actually, not question number 5. I believe in your notes, it is also question number 6. Will iodine oxidize Fe2 plus and Fe3 plus? Again, you have to get the correct species of iodine. When the question mentions iodine, it is referring to I2, not I minus, because I minus is iodide. Okay, iodine is I2. And again, I've got the relevant half cells, but this time they are not arranged from the most positive to the most negative, but still the same, because this is the more positive. I know that Fe3 plus will be a strong oxidizing agent, and 2I minus will be a strong reducing agent. Okay, strong oxidizing agent, and this is a strong reducing agent. So the question is now, will iodine react with Fe2 plus? So if you look at iodine and Fe2 plus, iodine is a weak oxidizing agent. Fe2 plus is also a weak reducing agent. So qualitatively, I can say that they do not react. Okay, they don't react. But now we want to do it quantitatively. Okay, so first things first is to write down the equation. Okay, so reduction and oxidation. Okay, now you have to be careful, even though the Fe3 plus and Fe2 plus, how do I answer this question? Maybe I don't do that first. Okay, so I will just say iodine reacting with Fe2 plus question mark. Okay, so because by qualitative investigation, we can already see that they probably will not happen. Okay, so just label that I2 is a weak oxidizing agent because of the value, and Fe2 plus is a weak reducing agent. I should have labeled that earlier. Okay, right. Now, so if we were to calculate the E cell, okay, we want to prove that it doesn't happen. Okay, so we know that when iodine reacts, it would be reduced to 2I minus. Okay, and that value, reduction, is positive 0.54. Okay, and then Fe2 plus, of course, the only possible route for the Fe2 plus would be to go to Fe3 plus. Now my equation is not balanced. Please bear in mind, it is not balanced. And that's fine, because this reaction is not going to happen anyway, so I will not bother writing down reduction and oxidation reaction separately. Okay, so Fe2 plus to Fe3 plus is an oxidation reaction. And because it's an oxidation reaction, it would have a value of negative 0.77. So if I were to calculate the E cell, E naught of reduction plus E naught of oxidation, I think most of you would be able to see it already at this point. Reduction is plus 0.54, oxidation is negative 0.77. Okay, so that's negative 0.23. Okay, so that means this reaction doesn't happen thermodynamically and based on its potential difference or E cell values. Okay, so this reaction is not feasible. Okay, so you really have to follow the question. Is the question talking about iodide reacting with Fe3 plus, in which case it would happen? Or is it talking about iodine reacting with Fe2 plus, which will not happen because it's a combination of a weak oxidizing agent and a weak reducing agent? And another proof that we can use is that the E cell values is a negative number, which suggests that this reaction is not feasible. Okay, so I've also made state that this equation is not balanced. I could make it balanced by putting 2 moles of Fe2 plus and 2 moles of Fe3 plus. Okay. Right. Next question is question number 7. Will hydrogen peroxide H2O2 reduce acidified manganate MnO4 minus to Mn2 plus? Okay, so again, I've selected out the correct half cell equations. Okay, so I should be picking out a half cell that contains H2O2, and I should also pick out a half cell that contains MnO4 minus and Mn2 plus. Okay. Right, I will move on now. Okay, so this are arranged according to the most positive to most negative, and I can highlight my strong oxidizing agent and my strong reducing agent. Okay, so these two highlighted are my strong, oxidizing agent, and H2O2 is a strong reducing agent. So even without doing calculation, I can already say, yes, manganate would react with H2O2. Now, if it was the reverse, Mn2 plus reacting with oxygen, it will not happen because Mn2 plus is a weak reducing agent and O2 is a weak oxidizing agent. Okay. Okay, so reduction and oxidation. So MnO4 minus, of course, the only possible way for it is to undergo a reduction reaction to form Mn2 plus. So I would write it as MnO4 minus plus 8H plus 5 electrons to form Mn2 plus 4H2O. And this E note is, the value is plus 1.52. Okay, next oxidation reaction is the H2O2. Of course, H2O2 doesn't have any other possible route, so the only reaction that it can undergo is the oxidation reaction, which means H2O2 would be oxidized to oxygen plus 2H plus 2 electrons, and the E note values for this is negative 0.68. So you just have to be careful with the sign here because we're looking at the reverse reaction, therefore the E note value would also be reversed sign. Before I can combine these two equations, half equations, I have to look at the number of electrons first. So the common factor for these two would be 10 electrons. Okay, so to make it 10 electrons, I need to multiply reduction by 2, and this one I need to multiply it by 5. Okay, so that means I've got 2 MnO4 minus plus 16H plus 10 electrons to form 2 Mn2 plus 8 H2O. And for the oxidation reaction, I have to multiply it by 5 to form 5O2 plus 10 H plus also 10 electrons. So can you spot now that I've got the same number of electrons? So then I can combine them to an overall equation. Notice that even when I'm multiplying my equation, my E note doesn't change. It stays the same. So overall equation is just literally adding a reduction and oxidation, all the products on one side and all the reactants on the other side. So 2 MnO4 minus plus 16H plus 10 electrons plus 5 H2O2 to form 2 Mn2 plus 8 H2O plus 5O2 plus 10 H plus 10 electrons. So you can see that the electrons will nicely cancel out, and then you just tidy up your whole equation. Okay, I will now move on to my E cell, which is the sum of my reduction and the sum of my oxidation, in which case I have 1.52 times negative 0.68, which should work out as 0.84. Okay, so this is a will hydrogen peroxide. Yes, the E cell is positive, which suggests reaction is feasible. Okay, so that means manganate can, hydrogen peroxide can reduce manganate ions into Mn2 plus. Now, if we were looking at, if you remember the statement, if the forward reaction is feasible, okay, forward reaction is feasible, the reverse reaction must not be feasible, okay? Why? So we'll have a look at Mn2 plus and O2. Okay, Mn2 plus and O2. Why Mn2 plus and O2? Because these are the ones that actually gets oxidized or reduced in the reaction. Okay, so you can see that Mn2 plus is your weak reducing agent, and O2 is the weak oxidizing agents. So even without calculation, we can already argue and say, well, Mn2 plus is a weak reducing agent and O2 is a weak oxidizing agent, so they will not react. It is not feasible. So that means this reaction happening or going in the reverse direction will not be feasible. Okay, I hope that is clear to you. Use the E0 value for the hydrogens. Explain the following: why bromine can oxidize in aqueous solution of iodide ions. Why bromine does not react with chloride ions. Okay, let's see. So first we want to answer why bromine can oxidize aqueous solution of iodide ions. So again, understanding the question, bromine can oxidize iodide ions. So why Br2 can react with I minus. Okay, so if we just look at these two equations first for now. Okay, so we know that bromine is a strong oxidizing agent and I minus is a strong reducing agent. Okay, so qualitatively, we can say bromine can reduce, bromine can oxidize, not reduce, can oxidize iodide ions because Br2 is a strong oxidizing agent and I minus is a strong reducing agent. Okay, but in terms of numbers, we're going to again do the E cell quickly. Okay, Br2 to 2Br minus, that's reduction with a value of plus 1.07. I minus, 2I minus to form I2, just quickly, oxidation. If you look at the oxidation value, it will be negative 0.54. So 1.07 plus negative 0.54, you should get (0.53). Positive 0.53 volt, which is positive, therefore feasible. Okay, so we are now going to answer the second part of the question. I will duplicate this page. How do I duplicate this page? Okay. So I'll let you copy this down first. Okay, next part of the question is to explain why bromine does not react with chloride ions. So again, bromine, Br2, chloride ions is Cl minus. So we look at bromine and Cl minus. So bromine is a weak oxidizing agent and chloride is a weak reducing agent. Okay, qualitatively, we can say Br2 is a weak oxidizing agent and chloride is a weak reducing agent. So that's quite self-explanatory why they don't react or not feasible. In terms of numerical or in terms of the E note values, we can find the E cell or we can explain it in words. Okay, so we say that E note of bromine is less positive than E note of chlorine. So we say that bromine bromine does not want to proceed in the forward direction. Okay, so bromine is less likely or readily to accept electrons and to be reduced. Same thing for chloride ions. Cl minus is more positive therefore Cl minus is less readily to release electrons. Okay, so if this E naught value was negative or less positive, then it would like to proceed in the reverse direction. But this one, no, they do not like to proceed in the reverse direction. Okay, so the explanation can be a little bit confusing. Okay, so I'll just repeat that and make sure you understand what I'm saying. So the E note of bromine is less positive than the E note of Cl2. Okay, so bromine is less likely to accept electron and to be reduced. So that means bromine doesn't want to proceed in the forward direction. As for chloride ion, okay, this number is more positive. It likes to proceed in the forward direction. Okay, but here we're saying that chloride will be oxidized to chlorine. And of course, because of the high positive E note values, oxidation reaction will less likely to occur because of the highly positive E note values. Okay. You can also find the E cell, of course. So there are three ways of E cell would be bromine going forward is a reduction reaction plus E-ox. So reduction is bromine to bromide plus 1.07. And oxidation would be the chloride to the chlorine, which is negative 1.36. So you can see that 1.07 minus 1.36 is negative 0.29. So that means because it is a negative E cell, therefore a reaction does not happen, doesn't occur. Okay, so that means bromine cannot react with chloride, but can chlorine react with bromide? Yes, because chlorine is a strong oxidizing agent. Bromide is a strong reducing agent if we're only looking at these two. Okay. So what E naught values can tell you is that who can be reduced and who can be oxidized. If the question is not asking, but if we're looking at chlorine and iodide, can chlorine oxidize iodide? Yes, chlorine is a strong oxidizing agent. Iodide is a strong reducing agent. So yes, chlorine can oxidize iodide to form I2 and Cl minus. Okay, so it's really helpful if you get access to all these half equations, but I'm not entirely sure if you are given the whole list or in the exam, or you're only going to be given whatever half equations you need to answer a particular question. Okay, so I will give you a few minutes to copy this down. And then we will finish off with the last question, question 9, which is to write the equation for the overall reaction of the electrochemical cells of Ag plus and Ag plus Ag half cell and zinc 2 plus zinc half cell. So again, to start off with question 9, you need to select your correct half cell equation. You already know how to do this. To write down the full equation of a reaction or of an electrochemical cells, you need to work out the reduction reaction and the oxidation reaction separately, and then you add them both. Okay, so let's try that. Ag plus Ag, which it should be at the bottom, sorry, at the top, because of Ag, they are arranged alphabetically. I have said this so many times already. And we need zinc 2 plus and zinc, which would be at the bottom, I believe. Yeah. Zinc 2 plus and zinc. Okay, so I already know that the most positive would be on top and the most negative would be at the bottom. So I can label, I know that the Ag plus is my strong oxidizing agent and my zinc is a strong reducing agent. So that means silver ion will be reduced to Ag and my zinc metal will be oxidized to zinc 2 plus. Okay, if you're good at this already and you're confident and you can see it straight away, you multiply this by 2, then you can straight away get to the final equation. Okay, so let's see if I were to do this. But even so, I have to be careful as well because I know I tend to make mistakes. So final equation, I'll start in reverse first, okay, and see if you can do this straight away in the exam. So full equation will be the reduction of my Ag plus to Ag plus zinc, okay, to form Ag plus zinc 2 plus. There, I've made a mistake, 2Ag, okay, because I've multiplied them already. All right, so how did I get that? Start with reduction. Reduction is the forward reaction, Ag plus electrons to form Ag. And oxidation is zinc being oxidized to zinc 2 plus 2 electrons. And again, my electrons are mismatched. So I have to multiply this by 2. This becomes 2Ag plus 2 electrons to form 2Ag. So then only because of your correct number of electrons, you can add them. You cancel out any electrons that are balanced or same on both sides. You should get this final equation. And quickly, okay, if you don't need to do this step, you can of course go straight to the final step, provided that you can do this confidently and correctly. Okay, if you think you're going to drop the stoichiometry numbers somewhere along the line, then don't risk it, because this is an easy, well, it is easy 1 mark question, but because sometimes we tend to make careless mistakes, even for myself, then we can just lose this mark easily. All right, so that is the end of this lesson. Just one last slide. Oh, no, no. So the point of this exercise are, we go back to this slide where here. Okay, so E cell means they are feasible. Stronger reducing agent will react with a stronger oxidizing agent. And also, if we saw that the forward reaction is feasible, then the reverse reaction is not feasible. And this is also true for the opposite. If the forward reaction is not feasible, then the reverse reaction is feasible. For example, where is this one? So iodine will not react with Fe2 plus because the E cell is a negative number, so they are not feasible. However, if we react iodide and Fe3 plus, okay, that is feasible, right? So this time the reverse reaction is feasible, because if you look at I minus, which has a value of negative 0.54, and Fe3 plus, 0.54, I minus, so I minus would go in the reverse direction. You change the value to negative 0.54, and Fe3 plus, of course, will go in the forward direction. It becomes 0.77. So quickly, if we were to do this quickly in our head, 0.77 minus 0.54, it will still be a positive number. Okay, so we've got like a few things left. I was hoping that I can cover this so that in the next lesson we'll jump straight to using the Nernst equation. But I think the last 2 parts, which is using the formula, as long as you use the formula correctly, then you should be okay. Right? But I don't want to rush doing E-note values versus concentration here. So we'll do that in the next lesson. Okay, Assalamu alaikum, and thank you, everyone.